So we have one more pure energy topic to talk about before we shift gears and go to momentum next week and talk about collisions. And that is the idea of rolling energy. When an object is rotating, it has some additional kinetic energy that is beyond the regular 1/2 mv squared kinetic energy that we're used to dealing with. So in order to get a way to calculate that, we need to think about rotation very briefly. And the way we measure rotation in physics is with this quantity rotational speed. And it's symbolized by the Greek lowercase letter omega, which looks like a curly W. And this omega, in order for our equations to work out right, should be measured in radians per second. And the idea of omega is very similar to the idea of speed. Omega is just the change in angle, theta, versus the change in time. And since we want omega to be measured in radians per second, that means that our theta should be in radians. And we actually don't have to use the theta when we talk about rolling motion and rolling energy. So it's all of these details will end up getting swept under the rug later. I just want to make sure that you understand that there's a straightforward foundation to all of this stuff. Now, when it comes to calculating an actual energy due to rotation, it involves this quantity omega, which is speed. And remember that our regular kinetic energy is 1/2 mv squared. So our formula is going to involve omega squared. But our formula also has to have something related to mass. And it's, as it turns out for rotation, that mass-like quantity is a little bit different than just pure mass. It's called the moment of inertia, and it involves not just the mass, but the physical size of an object. So if you take an object with mass, like this pen, and you rotate it around its own axis, then the entire mass of the pen is concentrated in at a very small distance, and it's actually very easy to rotate back and forth. On the other hand, if you take the same object and rotate it about a different axis, you can feel that it is more difficult to rotate that object back and forth. And that's because of the physical size of the object from the axis of rotation. This pen is a much larger distance from the axis of rotation that I'm rotating it around now when I flick it back and forth between my fingers than if I rotate it around its own axis just by rolling it between my hands. So for actual rollable objects that you could put on an incline and they would roll downhill, it turns out that this moment of inertia quantity is always proportional to the radius squared. In fact, it is equal to mr squared for ring. If you think of a hollow cylinder or a ring rolling downhill, then the moment of inertia is just mr squared. If that cylinder or ring is solid, then that moment of inertia becomes 1/2 mr squared. And that would be for a disk. So the difference between these, again, is that the ring is hollow in the middle and the disk is solid all the way through. And for the disk, there's more of the mass in close to the center. So the actual kind of average radius is a little bit smaller, and that's why there's a factor of 1/2 there. Because this capital R is the outer radius. So the actual radius of materials in a disk is a little bit smaller. Of course, you don't have to have a cylindrical object or a two-dimensional object like the ring or the hollow pipe are the same thing, or the disk and a rolling log, a dowel or something, are the same thing. You can also have spherical objects, three-dimensionally round objects. And for those, we have similar formulas. There's a 2/3 r squared, and this is for a hollow ball, and a 2/5 mr squared for a solid sphere. I may be getting my mathematical terms mixed up. A ball and a sphere, mathematically, one is supposed to be solid and the other's hollow, and I forget which is which. So I just put the word there and say that the hollow one has the 2/3 mr squared and the solid one has the 2/5 mr squared. So all of these fit a pattern. Where the moment of inertia is equal to some proportionality factor that I like to call A over B times mr squared. And that A over B is just representing a proportionality factor between the actual moment of inertia, capital I for that object, and the mr squared value. And note that for the ring, that fraction is equal to 1. For the disk, it's 1/2. For the hollow ball, it's 2/3. And for the solid sphere, it's 2/5. So we have different fractions, A over B, for different types of objects. So how does all this go together to tell us the kinetic energy? Well, our kinetic energy is just 1/2 times I times omega squared. And note the similarity between this new rotational kinetic energy, 1/2 I omega squared, and the original translational kinetic energy, 1/2 mv squared. So they're very similar formulas. Now, the next step we need to take is to think about a rolling object. An object that is rolling without slipping has both translational and rotational energy. And I have some drawings that I'm trying to copy and paste here. So, come on, there we go. All right, copy to the clipboard and paste. And I don't need that text anymore. And I want these to go up here. Come on. And that guy's going to stay down there. Okay, so the rolling object has translational velocity. That is, the entire object is moving, so the center of mass is moving, and this point that touches the ground is moving. So that's the velocity caused by rotation. And the rotating object, if it was purely rotating, would have the center of mass be not moving, and every point on the outside would be spinning around and around and around. And the speed speed of any given point on the object is just the rotational speed, omega, times the radius of that point on the object. And the rolling object actually involves a point at the bottom that is not moving at all. So when we combine this together, we find that the required omega is equal to the that's how much rotational speed the object has to have. So it's not spinning too fast and doing kind of a burnout, but it's not spinning too slow and just skidding. It's the just right speed of rotation. So now let's take a look at this kinetic energy of rotation. It's 1/2 I omega squared. And that is 1/2. And let me put in my little pattern formula for I. A over B times mr squared. So that's my I value. And then let me put in my omega value, V naught over R squared. Notice here that we have an R squared here, and we have an R in the denominator that is squared because of the parentheses. And that R squared, that's part of the I value, and the R squared that's part of the omega value cancel each other out. And this whole thing turns into A over B times 1/2 m V naught squared, which, by the way, is just A over B times the kinetic energy of translation. So let me say that again. That rotational kinetic energy is literally just proportional to the translational kinetic energy. So how do we use this? So let's consider a situation, and we'll put our object on an incline, and there is the bottom of the hill, and this object starts with a certain height, h, and we'll say release from rest. So when I figure out what's going to happen here, I want to think initial energy plus work due to any force for which I don't have potential energy is equal to final energy. And my initial energy is going to be potential energy due to gravity. And I don't have any work here because the only forces involved are gravity, which is taken into account with the potential energy. The normal force doesn't do any work because work requires a force and motion in the same direction. And with this incline, the normal force and the motion are perpendicular to each other. There is a friction force of grip, but the grippy friction force doesn't do any work either because that point isn't moving at all. This point of contact where the grippy static friction force happens isn't moving. So there's no energy consideration there either. And then our final energy is we're going to have our kinetic energy of translation plus the kinetic energy of rotation. So this is going to be mgh, because potential energy is always mgy, and our y value is going to be equal to h. And we're going to have our 1/2 mv squared plus, and we're going to need an a over b times 1/2 mv squared. So as you can see, the initial energy now has to get split up and shared between these two different types of final energy, these two different types of kinetic energy. Some of it's going to end up as regular 1/2 mv squared translational kinetic energy, and some of it's going to be the rotational kinetic energy, which is proportional to 1/2 mv squared. So let's see how I end up solving situations like this. So let's make it a hollow ball, which means that I equals 2/3 mr squared. There we go. And h equals, let's go with 25 centimeters, so 0.25 meters. And that's it. Well, let's do m equals 0.6 kilograms so that we have a specific mass. So then the first thing I would do is I would calculate mgh is 0.6 times 9.8 times 0.25. So let me record stuff. 0.6 of mass. Height is 0.25, and mgh is the mass times 9.8 times the 0.25 is 1.47 joules. 1.47 joules. So that's what's going to go on the left-hand side. 1.47 equals. Now, what I want to do is break this solving into two parts. I'm going to call this K for kinetic energy of translation. And we're going to have this fraction, A over B, which is 2/3 K. That thing right there, that's K. And that 2/3 is our A over B value. A over B equals 2/3. It's the proportionality factor for the purpose of calculating moment of inertia if you needed to calculate that. But it's also the proportionality factor for the purposes of dealing with kinetic energy of rotation. That A over B stuck around through this entire thing. A over B is inside the moment of inertia. So then I can use this for K, because if I have 1K, this is 3/3 K plus 2/3 K then that is going to be 5/3. K is 1.47. So now to solve for K, I just multiply both sides by 3/5. 3/5 of 1.47 is equal to K. So A over B is 2/3, and then K is equal to that over that, which is that over that plus 1 is 0.882 joules. So now we know the regular translational kinetic energy, and I can then find out the kinetic energy of rotation. Ke of rotation is equal to A over B times Ke translation. And in this case, it is 2/3 times 0.882. And that is, that times that is 0.588 joules. And note 0.882 plus 0.588 is equal to 1.47 joules as required. So now the last step is I can figure out the speed at the bottom, because K is equal to 1/2 mv squared. So my 0.882 is equal to 1/2 times the mass, which is 0.6 times v squared. That means that v is the square root of 2 times 0.882 over 0.6. So v is square root of 2 times the regular kinetic energy over the mass, which is 1.71 meters per second. So that is the basic idea of the rolling energy analysis. I want to make one more qualitative observation before I close down the lesson here, and that is the bigger our kinetic energy of rotation is as compared to the Ke of translation, that means that there's less initial energy left over to be equal to 1/2 mv squared. In this particular case, we had 1.47 joules of initial energy, but of that, 0.588 joules were allocated to the rotational energy, and that only left 0.882 joules to be equal to 1/2 mv squared. So the rolling object ends up moving more slowly at the bottom of the hill. So that's the general idea of rotations, and hopefully that gives you enough of a clue as to how to answer the homework questions about rolling. And with that, I'm going to close down the recording.